Hello, hello. Um, Welcome to a new devlog. Uh, I don't know. I think this is the number 9 or 10. Yesterday we reached out to exercise 71, and let's pick it up from there. So, exercise 71. There have been several instances where it would have been nice to use loops in our programs, but we couldn't because the things we were trying to do could only be done at compile time. We ended up having to do those things manually, like normal people. We are programmers. The computer should be doing this work. An inline for is performed at compile time, allowing you to programmatically loop through a series of items in situations like those mentioned above, where regular runtime for loop wouldn't be allowed. Okay, this I remember there were some examples of creating characters of the game, and they were defined outside of the main loop in the body of the program in the main context, and they were repeating themselves. Yeah, probably this is referring to that, right? And then we have this inline for that is suggested could replace those. What is the syntax? We say inline and then for, then we have a series of types. Okay, this is similar to the normal for loop, right? And here we are iterating over types and then getting them one by one, and then we can print them. In the above example, we are looping over a list of types which are available only at compile time. Okay. What is the error? We have question marks. Okay. Remember Narcissus were from exercise 65, where we use built-ins for reflections. He's back and loving it. Okay, we have Narcissus. Narcissus has room in his heart for. Last time we examined Narcissus' struct, we had to manually access each of the 3 fields. Our if statement was repeated 3 times, almost verbatim. Yeah, please use an inline for to implement the block below for each field in the slide fields. So we have fields. It would be inline. Do we need to be inline here? For iterate over fields, yet field. Once you've got that, go back and take a look at the exercise 65 and compare what you've written to the ambition we had there. Okay. Type info. Is this because these? Okay, I think this will fail, right? Yeah, this will fail because of the comptime values that we have here, right? Type info should be comptime known. That's why we cannot use a for loop. And if we inline it, it will solve. And now let's open 65. Down here we had 3 if statements, which we couldn't use the for loop with because of that. Okay, this I didn't notice when I was solving this program, this exercise. So yeah, this is interesting. If you have a comptime value that you want to iterate on, you need to use the inline for loop. But what does it do differently? When you do inline keyword, I assume the compiler will actually make 3 versions of this if statement, basically. An inline for is performed at compile time, allowing you to programmatically loop through a series of items in situations like those mentioned above. Okay, interesting. Oh, I didn't clean this up. Let's clean it up, and then number 71 sold. Let's do 72. There is also an inline while. Just like inline for, it loops at compile time, allowing you to do all sorts of interesting things not possible at runtime. See if you can figure out what this rather bunkers example prints. So, const foo, we have, okay, 3 print templates, comptime where I equals 0, while who I, yeah, basically 3 new lines with these templates, and for each of them we are putting 0, 1, 2. You haven't taken off that wizard hat yet, have you? No, I have a sorcerer hat, right? Okay. We have question marks to fill in. Here is a string containing a series of arithmetic operations and single-digit decimal values. Let's call each operation a digit pair and an instruction. Let's call each operation and digit pair an instruction. I cannot read this morning. Okay. We have 4 instruction, and then here is a u32 variable that will keep track of our current value in the program at runtime. It starts at 0, and we will get the final value by performing the sequence of instruction above. So it will be 3, 15, 13, 26. This index variable will only be used at compile time in our loop. Okay. Here we wish to loop over each instruction in the string at compile time. Please fix this to loop once per instruction. So again, I want to first make the error to see it. Okay, go here, and then what I need to do is to I plus equal 1. This gets the digit from instruction, Can you figure out why we subtract 0 from it? This is rather interesting, right? Here what we are doing, we want to get the digit out of it, right? But here we don't have, we're not using a list. The type indicates that and we are subtracting a 0 out from it. Let's first do this. I will figure this out. Let's do it one by one. First, Zig build. Cannot store to comptime variable in non-inline loop. Yes. And then we do comptime. Oh no, not comptime, I want inline. And now, overflow of integer type u8 with value -16. I suppose it should have worked. This is the actual question here, why we are subtracting 0 from it. Overflow of integer type with value -16. I'll be right back. I need to interrupt for a moment. Okay, I'm back. So, what is the problem here? We are getting overflow of integer type u8 with value -16. Where is this -16 coming from? Okay, let's read further if there is a problem. This switch statement contains the actual work done at runtime. At first, this doesn't seem exciting. Which line is it? It's line 42, this exact line, right? And then, but it's quite a bit more exciting than it first appears. The inline while no longer exists at runtime. and neither does anything else not touched directly by runtime code. The instructions string, for example, doesn't appear anywhere in the compiled program because it's not used by it. So in a very real sense, this loop actually converts the instruction contained in the string into runtime code at compile time. Yes, we are compiler writers now. See, the wizard hat was justified after all. Um, but I don't get what does it mean here that this loop actually converts the instruction data string into runtime code. What does it mean? But I want to figure out what it looks like, right? In runtime code. Let me take a note. Runtime code. Okay, I will get back to that, but for now, why I cannot solve this one? Here we wish to loop over overflow of integer type. Okay, I think this is the time that I will ask Copilot to help me. Not like that. Wanted GPTL. Yes. In the following program, why I'm getting an overflow error. U8. Let's make it challenging for it as well. Not indicating which line. For now, let's see what does it do. The overflow error occurs because you're incrementing I by only one in each iteration. Yeah, now I get it. That's why. What I was thinking. There are three correct characters every time I need to go forward with, and this -0 that now this is sold, and when you do on a space restart, you get values outside the range. Y increment by 3. Yeah, that I understand. Can you also explain what -0 is actually? Absolutely. It's a clever way to convert a character digit to its numeric value. How it works. In ASCII and UTF-8, digit characters are stored as consecutive values, and so on. Okay. Oh man, this is really nice. The conversion, this if instructions is I plus 1 is 3. Okay. 3 has ASCII value of 51. Then 0 has 48. And then 3 minus 0 is giving us 3, the actual number. Why this works? ASCII digit characters are consecutive starting at 0. Subtracting the base 0 gives you the offset, which equals to the digit value. It's a standard idiom in many programming languages. Alternative approach. The zero trick is concise, fast, and works for any single digit character. This is interesting. I never thought of it. So basically what it does here, we have a U8, and when we pick this up, a U8 character of 32 is up 3 is actually 51, right? So the value down here, the digit of U8 would be 51. We're subtracting it by 0 and we get the 3, the actual value. Okay, very interesting, very interesting. Let's solve another one. This took quite long, but I learned something. That's a good sign. Uh, 73. As a matter of fact, you can put comptime in front of any expression to force it to be run at compile time. llama. Get a value, execute a function, execute a whole block. Get a value from a block. Okay. Unable to evaluate comptime expression. We want to fetch the last llama. Please fix this simple mistake so the assertion no longer fails. Unable to evaluate comptime expression. This is the comptime expression. So does it mean since Dan has a comptime value, I need to also do comptime here? No. Oh, actually that was a different thing. Unreachable code. If okay. We put a guard assert at the top of this function to prevent mistake. The comptime keyword here means that the mistake will be caught when we compile. Without comptime, this would still work, but the assertion would fail at runtime with a panic, and that's not nice. Unfortunately, we are going to get an error right now because the I parameter needs to be guaranteed to be known at compile time. What can you do with the I parameter above to make it do so? I don't get it. So this is, I think, what it needs, right? Because we want this parameter to be known in comptime. We've done it before. We are doing comptime, but why the error is it? Fun fact: this assert function is identical to from the Zig standard library. Bonus fun fact: I accidentally replaced all instances of foo with a llama in this exercise, and I have no regrets. Yeah. But if not, okay, you're getting. Okay, we are passing 5. Llama count is 5. Get llama 5. Should I change this to make it? Yeah, but then do I need this? No. The background exercise 073. No, that comptime wasn't necessary. Okay, the mistake here, I was confused. The mistake here was the index, not the use of comptime. But when I used that, it was just processing calling that function on comptime. But it was no use here because the thing I wanted to check at comptime was this assert, and that needs this I to be evaluated at comptime. This is interesting. So if I want to assert the condition of my program at compile time and not get surprised at runtime, this is how I do it. '73. Done. Let's start with 74. In addition to knowing when to use comptime keywords, it's also good to know when you don't need it. Like in the previous example where I was actually calling comptime for a function that I didn't need it for. The following contexts are already implicitly evaluated at compile time, and adding the comptime keyword would be superfluous, redundant, and smelly. The container level scope outside of any function in a source file. Type declaration of variables, functions, struct, unions, enum. The test expression in inline for and while loop, an expression passed to C import. And I assume one more thing can be added here. Any function that already has a compile time as only the assert part here is going to be executed as compile time value, right? I don't think this is going to be a compile time thing, or no, here the argument passed to it is compile time required. So the only line that is not compile time required is this. And that also is using a compile time value. No, but this is, I think, runtime. It's in the morning and I'm sneezing. Yeah, let's continue. Work with Zig for a while and you'll start to develop an intuition for these contexts. Let's work on that now. You've been given just one comptime statement to use in the program below. Here it is. Just one. Just one is all it takes. Use it wisely. Okay. Being in the container level scope, everything about this value is implicitly required to be known in compile time. Okay, again, this value's type and size must be known at compile time, but we are letting the compiler infer both from the return time of function. Okay. And here is the function. Note that the return value type depends on one of the input arguments. We have count, user. Okay, and then we are returning the array of, okay, this is where we put the comp type. It's obvious, right? Because we are returning the type, then no, that should be known in compile time. Zig build. 74 is already passing. Zig run exert sizes 0.74. Okay, there is no error here. Interesting. Note that this doesn't need to be an inline while. The lesson here is to not prepare your program with comptime keywords unless you need them between the implicit compile time context and the aggressive evaluation of any expression it can figure out at compile time. It's sometimes surprising how few places actually need the keyword. Okay, so far I was thinking every time we are going to return a type, that type should be known at compile time. But apparently here it's not required anymore. Because llama count is known in compile time, and make llamas also invoked in compile time. What happens if I... Sorry for sneezing, this is in the morning, I cannot help with that, but what happens if I run this from within the function? Exactly. This is what I was looking for. So it was considering it a compile time value and evaluating it in compile time because it was outside of body of any function, right? It was the main context of the program, and there we know it's going to be processed at compile time, and there it knew the count function, so it's going to process all of it at compile time. But if I move it inside the body of a function, it will raise this error. Interesting, interesting. And there I can process it at compile time explicitly. Number 74 also solved. Let's do one last one. 75, quiz time. Let's revisit the Hermit map from quiz 7. Oh, don't worry, it's not nearly as big without all the explanatory comments, and we are only going to change one part of it. Alright, links must be compile time known. Remember how we didn't have to declare the numeric type of the place count because it is only used at compile time? That probably makes a lot more sense now. Yeah, it does. Okay, so as you may recall, we had to create each pass struct by hand, and each one took 5 lines of code to define. Well, armed with the knowledge that we can run code at compile time, we can perhaps shorten this a bit with a simple function instead. Let's fill the body of this function. Okay, make pass. I think it should be return pass, and then from full to, it would be like this, equal to from 2 equal to 2, and this equal to this. And here we are going to have this. Number 75 also solved, so it's quite an easy one. But I have a question still. Why on the previous exercise, previous quiz, which is quiz 7, we were doing this part manually? So we had this place, no, it was passes. We had this pass. We were setting them manually. But over here, where we didn't have to declare the numeric type of, yeah, that's irrelevant, I believe, to this. And then we have a function here. Oh, but is it more readable? We've seen that it is possible to uh, parse strings at compile time. So the sky's really the limit on how fancy we can get. For example, we could create our own pass language and create passes from that, something like this perhaps. Feel free to implement something like that as a super bonus exercise. Okay, I want to finish this stream here, but I would like to get back to this. There are a few things I don't understand. First, um, why it's different now? Why on the previous quiz, I couldn't have a function like what I have right now? This make pass function, why it wasn't possible? And then the second, how it's possible to create this syntax? Would be interesting. Okay, thank you for watching. Let me know if you have more details about these, and see you in the next one.